Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss a very important topic of magnetism which you have heard already. It is called as Hall effect. Now you can see that there is a cuboidal shaped conductor which is connected through a battery, and the current is flowing in this sense like that. Okay, and let us suppose that current is I. So I will be equal to NEAVD, where A is the area of cross section and VD will be the drift velocity of the electrons, which is the average velocity of the free electrons with which they move through this conductor. So first of all, let us see that the value of current I is NEAVD, and A is the area of cross section. In this case, the cross sectional dimensions are A into B, so the area of cross section will be A into B. So I will be equal to NEAB into VD. So I will be equal to NEAB VD, where N is the number of free electrons per unit volume, is the electron charge, and VD is the drift velocity. These are all the material based things, and A into B is the cross section dimensions. Now we know that as these electrons will be moving in the backward direction, and if we apply a magnetic field on this arrangement in the upward direction, let us suppose that we have applied a magnetic field in the transverse direction. Transverse means in the perpendicular direction of the current flow. So current is flowing like that, and we have applied a magnetic field like that. Now if we observe this conductor through the top view, if we draw the top view, so from the top you can imagine that magnetic field will be in the dot sense, which means that magnetic field will be coming out of the paper. Okay, and the current will be flowing from this end to this end. So current is flowing like that. This is the direction of flow of current. Now if we talk about any one electron, then we can see that this electron will be moving in the backward direction with a velocity called as drift velocity, and this electron, as it is moving in a magnetic field which is of magnitude B, so it would be experiencing a magnetic force whose direction can be predicted by the Fleming's left hand rule. So you can apply the Fleming's left hand rule, and you can see that the direction of force acting on this electron will be in the downward direction. This will the magnetic force, and therefore these electrons will be getting deposited over this front face. Okay, over this face. So there will be a deposition of electrons over this face due to the magnetic force, and hence a opposite charge, which is a plus charge, positive charge, will be deposited on the other opposite face. And you can also see that an electric field will be developed like that. Now this dimension is A, so this is A, and due to this electric field which is developed in the downward direction, electric force will start to act on the electron in the upward direction, and this electron separation or deposition will saturate when Fe will be equal to Fb. Now Fe will be equal to E into E, and Fb will be equal to Q, which is E, V, which is drift velocity, and B is the magnetic field. Now the value of drift velocity Vd is equal to I upon NEAB. So the drift velocity is I upon NEAB, and this is magnetic field. Okay, so this is the electric field developed in the conductor, and this electric field is perpendicular to the magnetic field, as well as this electric field is also perpendicular to the direction of velocity of the electron. So hence we call this electric field as transverse electric field. So Hall effect says that when a current carrying conductor is being placed in a magnetic field, transverse magnetic field. Now this word transverse refers to the fact that magnetic field should be perpendicular to the direction of current flow. So if in such arrangement the current is flowing through a conductor, then the deposition of electrons will start to occur across the conductor on the opposite faces, which are perpendicular to the direction of flow of current. In fact, the faces are parallel to the direction of flow of current, and this deposition will saturate at the time when sufficient amount of electric field would be developed across the conductor, which would cancel out the magnetic force. So the Hall voltage, Hall voltage, which is developed across these two faces, can be calculated as E into D, or E into this distance. This distance is A. So the Hall voltage can be written as I into B upon NEB, cancelling A with A. So this is the Hall voltage, and this effect of deposition of electrons across the conductor when that conductor is being placed in a transverse magnetic field is called as Hall effect, and the voltage developed due to this deposition is called as Hall voltage. So now we will discuss some more concepts in the next video. Thank you.